Okay, so we're at the last section of Chapter 3. Title is Exponential and Logarithmic Models. So we're just going to talk about some general exponential models and what applications they have in real life. So here to the right we have kind of your generic exponential growth situation. So y is the dependent variable, x is the independent variable, and you have a constant b which is multiplied by x. That tells you how quickly it grows. The larger b is, the larger positive b is, then the more quickly the value, the quantity grows. And b has to be greater than 0 for an exponential growth. We'll find out when b is less than 0, you'll have exponential decay. And a has to do with what the initial amount is. So if you start with more, you end up with more. But it's a proportional thing. If you have twice as much to start with, you're going to have twice as much at each value of time, given the constant b value. And here's an example of an exponential growth situation. So we've got 0.5 times e to the 2x. So if you think about in terms of stretching and things like that, you've got both a stretch and a shrink. So this causes a shrink in the y direction because it's 0.5. If it was 1, then it wouldn't be shrunk or stretched. And the 2x, what that does is it also shrinks it in the x direction. So so ultimately, let's look at compare this with y equals e to the x. So y equals e to the x has an intercept of 1, and then at x equals 1, this is for this, y equals 2.71828, and then at x equals 2, it's way up here. And then here at x equals -1, you have 1 over 2 point something, so it's around there. So you can see that they kind of cross over each other. But you'll notice that the value at x equals 0 is half for this one compared to that one. Because when you put x equals 0 into this expression, you get e to the 0. So this number is immaterial when x equals 0 because this is always e to the 0. So the thing that drives the value, the initial value, you might say initial, what does that mean? Well, usually, a lot of times this variable x is really t. T equals 0 would be the starting time. So you would never have anything happening here at negative time. Okay, so so here's an example of exponential growth, which is population. And so this is a cartoon of human population growth chart, including projections. So what they're showing here on the x-axis, it's a linear, it's a linear scale. Each mark is 200 years, and here we are at 2000. And I'm not sure when this cartoon was drawn. I think it says 1994, so it's close to 2000. And if you watch this growth, if you fit a curve to this experimental data, you'll end up with an exponential growth situation. And the problem, of course, with exponential growth is that at some point, even a small amount of time results in a significant increase. And this really only can happen when you have unlimited resources. At some point, you're going to run out of resources, whether that's land to live on, food to eat, and it'll end up either flattening out in the best case scenario or collapsing in the worst case scenario. So here's the two situations: exponential unrestricted growth. So you have a certain population birth rate, death rate, and the difference would give you the growth rate. And those values are independent of the percentages are independent of the population, and so it ends up growing exponentially with time. Now, logistic growth, where you have a limited capacity in terms of resources, what will happen is you'll grow exponentially to start with, and then at some point there's going to be limitations on what is available to drive that growth, and it's going to slow down and level out. So you might think of a deer herd that's introduced to some new environment, and initially the deer, there's few of them, and they have essentially unlimited potential for growth at that point because there's no competition for the food. So it grows really quickly, but then at some point food gets more scarce, so the deer become less healthy, and they start having either less offspring, or the death rate increases, and that slows down, and at some point you reach a kind of a equilibrium situation, and the population remains fairly constant. Now there's one thing, this is kind of a interesting fact. A lot of times with rabbit populations, what you see is something that happens kind of like this. You got a small number of rabbits, a lot of food, it increases, gets to here, and then it goes, and it does the same thing. And what drives this is typically a disease. And so as there are few bunnies, they have lots of more bunnies, and it grows. But at some point, you get overcrowding, and you're more likely to transmit disease, considerably more. And at this point, the whole colony gets infected, and almost all of them die off, except for a few. And then they start all over again. Once there's few rabbits, there's less chance for infection. And you probably could see that with, you've probably seen this with things like the Black Death in the Middle Ages. There was a big crash in population, not down to these levels, but now this is a lot of times when you have exponential growth, it's easier to plot one of the variables with respect to the log of the property. So here we have percent population growth, which is this is a linear scale, but here we're plotting the log to the base 10 of the GDP, gross domestic product per capita per person. And if I looked at this from just the GDP instead of the log of the GDP, it would look, it would have an exponential form. But by taking the log of the GDP per cap, it ends up being a straight line. So it's sometimes easier. Back in the old days, it was easier to plot the data on a log scale and then fit a straight line to that log data. And basically what it's saying is that, the higher the population growth for a country, the lower the GDP per capacity. So what we normally see is that places that are having a lot of kids tend to have lower okay. So what we're seeing here is that if you have lower GDP, that you have lower population growth, and at some point in the very wealthy places, you have they're wealthy, but they are their population growth is lower. So what we can do here is you can fit a linear curve to say this data, and then figure out what the changes. So let's just look at it. So what I did was I think I picked a point here at 3.3% population growth, and the GDP is so this is if you take the what am I doing here? I think these are the ones that are not where you're not taking the logarithm. So these are just two data points which are not applied to the logarithm. So what I have is I'm going to fit a straight line between these 2 points, which is probably 1 point here and 1 point up here. And you're going to say the population growth, which is this, the y-axis, is equal to a, which is going to be the y-intercept, plus b times the log of the income. So this is the x variable, which is the log of the income. And the slope is going to be, so this b is the slope here, is going to be delta y over delta x, the rate of change. So you take the delta y, which is this, and the delta x is going to be the log of these two, log to the base 10. So you get a slope of negative 1.5. And then you can take this one of those two data points, which you turn out to choose, I guess they choose this one here, 3.3% and $316. And you can figure out what the y-intercept is. And so then you get this linear equation that predicts the growth as a function of the log of the income, rather than doing it as an exponential result. Just sometimes more convenient. You don't see that done as much. Now, what you can do is you can take the linear equation, which is fitting this data, and then you can solve for the income here. So right now it's the log to the base 10. So this is a solution of a logarithmic equation. I'm solving for, this would be y and this would be x. So I want to solve for x. So what I do is I subtract 7.17 from each side, divide by negative 1.55, and then I have log to the base 10 of the income. I want to solve for the income. So I take, because it's a base 10 here, what I do is do 10 to the log base 10 of the income equals 10 to this 7.17 minus growth divided by 1.55, and 10 to the log base 10 is, that's their inverse function, so you just get income. From this you get income, and so you can see it's an exponential growth with the base being 10. Now you could do the same thing probably if you wanted to do, if you plotted instead of log base 10, you could do log base natural base. Now on the other end is what we would call exponential decay. So there you start with a value and the value decreases quickly at first, and then as time goes on it decreases less quickly. So the main example of exponential growth is things like population growth. Also, if you deal with investments and you have continuous compounding in a bank, those are both exponential growth. Exponential decay, you're thinking of things like the temperature of a thing as it cools in the air, radioactive decay. Radioactive decay is one of the big ones when it comes to exponential decay. And so if you also go back to look at this equation that I came up here, this graph, you'll notice that this is, growth is to the negative power. So in some ways this is actually exponential decay, not an example of exponential growth, even though it's not really decay. It fits an exponential decay curve. So this is the same. This is TFR. What does that mean? I'm not sure what that means. Okay, so exponential decay is exactly the same, except the exponent is a negative quantity. B is positive, so the positive times the negative, this is always a negative value times x. A is, again, based upon the initial conditions of the situation. Initial temperature, initial amount of radioactive material. And in this case, we're looking at the same curve, and as before, except we have a -2. And so because we have the negative here, but all the other numbers are the same, what this negative does is it's a y-axis reflection. So when we went back to exponential growth, basically usually you started at x equals 0 or time equals 0, and then it grew from that point. When you have exponential decay, you start with some value and it gets less with time. And the 1/2 sets the initial amount, and the 2 tells you how quickly it decays. So here's exponential decay for the isotope carbon-14 as a function of percentage. So you start at time t equals 0 years on 100%. After 5,730 years, you've got 50% of it remaining. This value, the number of years to reach half the initial amount, is called a half-life. And that's true for any exponential decay. It's the time where you have half the original quantity. And then what happens is, if you go 2 half-lives, you have the quarter of the original amount. And if you have 3 half-lives, then you're at an eighth. And it just keeps being cut in half every certain number of years. So by looking, the way this thing works is by knowing what percentage carbon-14 is when the organic living compound is created, you can measure the amount of carbon-14 in it after it has been, after it dies and becomes something like wood in a house or somewhere, or even just a body that's frozen somewhere. And you can calculate how old it is based on the percent of carbon-14. Another example is of exponential decay is the cooling of an object. So what you're looking at is you're looking at some object, say a solid object, and it has some temperature T, and at T equals 0, you drop this into some kind of atmosphere. It could be water, it could be anything. And assuming that the body changes temperature, but within it the temperature is the same at any instant in time, it's going to behave in this way. You can do the calculus to figure that out. T sub R is the temperature of the, I don't know what they have R standing for, but it's the temperature of the, we would call it the environment. And you're assuming the environment has enough mass that, if the environment has enough mass that it stays constant, so it's always the same environment temperature. So if you think of a cold glass of water, the atmosphere that's surrounding that would stay at the same temperature. As this cools off, that it's not going to warm up the environment. And what you'll see is that it decays in an exponential decay type situation. Another thing to look at is this situation where you have A constant times e to the minus x minus b squared over c. So a, b, and c are constants. X is the variable. And if you plot that, it looks something like that. So this is 0.5. And it looks like 0.5 might determine what the value is, the maximum value is. So you see it's 0.5, and that's 0.5. So that happens when this maximum occurs when the exponent goes to 0, and it goes to 0 when x equals 2. So you can see here x equals 2 is where you get the maximum 0.5. And this quantity here shows you how quickly it decays on either side. So if you had a different number here, 5 or 6, it either does it more slowly or more quickly. I'm not sure which one it is. So what has this behavior? Well, you have, in statistics, you have what's called a normal distribution of data, and it satisfies an equation like this Gaussian model, and the constants are a function of the mean. So A, B, and C are functions of the mean and the standard deviation. Now if you look at something like e to the x squared, you know, this thing's the exponent, which when you square it, it grows even more. But instead of going like this, it actually goes back up because you're squaring it here, which means that when x is negative, it's going to have the same, x squared is going to have the same value. So negative 1 squared is the same as positive 1 squared. So it has this symmetry around the y-axis. And here, so this is y equals x squared. If you look at, here's y equals e to the x squared. Here you have e to the minus x squared. So it takes this, and because you've got a negative sign, instead of growing exponentially this way, positive, it's going to decrease exponentially on either side. And when x equals 0, that means the exponent is 0. You get e to the 0, which is 1. So you can see how we're kind of approaching this situation. The additional terms affect where this thing is centered, and you can see that I have a translation in the x direction here of positive 2, x minus h, so h is 2, so I've displaced it horizontally. And these other two things affect how wide and how quickly things happen. So if I now put in x minus 2 in here, what that does is it shifts this over 2 units. So this is just an x-axis shift. And let's see what I do next. Next, I divide by 3. So that doesn't change the maximum. It doesn't change where the maximum occurs. It just spreads it out further. So the curve is not as sharp around this maximum. And then multiplying by the 0.5, what that does is it just moves everything down. And this is an example of a normal distribution. It is the IQ distribution. And the height of the curve tells you the percentage, gives you some idea of the percentage of people who have IQs between two values. It doesn't tell you what percentage of people have exactly 100 IQ, because nobody has an exactly of 100 IQ. So what you use these curves for, these normal distribution curves, is you look for the area underneath the curve, and that area gives you an idea of the quantity, the percentage between two IQ values. And what these colors are, this is plus what we would call 1 standard deviation. This is minus 1 standard deviation, which is usually 15 for IQ tests. So this is 85, this is 115. And then you go to 2 standard deviations both ways, and that is going to be 30. So this would be 130, and this would be 70. And there's approximately, I think, 63% maybe between 1 and 2 standard deviations, and about 95% between 2 standard deviations. So if you have an IQ greater than 2 standard deviations, you're going to be in the not in the 95%. You're actually going to be in the 97.5 percentile. 2.5% on this side and 2.5% on that side to give you a total of 5%. But this has what's called a bell curve shape, and a lot of physical measurements, whether it's IQ or weight or height or lifespan or things like that, tend to have a normal type distribution. We would call this our bell-shaped curve. And this gives you kind of an idea. This is using that particular bell curve, and it says that if you, with a standard deviation of 15 and an average of 100, that if you have an IQ of 132, that you're in the 94th percentile. And what that means is that you are have an IQ greater than 98.4% of the people. If you are an IQ of 130, you have an IQ higher than 97.72%. And then you come over here to the really high values. So an IQ of 150, you have an IQ greater than 99.96% of the population. There's a little joke here. So here's Mensa. If you're not familiar, Mensa is a organization that you can belong to that is for people that have an IQ above, I think, 140. And of course, if you're a woman, it's Womansa. Okay, so what we've done, we've looked at exponential growth, population, savings account, exponential decay, cooling, radioactive decay. We've got this normal distribution, which, what they call it, forgot the name, Gauss. Yeah, so you got the Gaussian model, and that's the most prevalent use of the Gaussian model is the normal distribution for data. You've got the logistic growth model, and this is the case where you have a limited environment in terms of the resources. So you grow quickly at first and then you level out. And we'll cover this again in calculus in a lot more detail. This is just an introduction to show you some of the applications of logarithms and exponents. But A is a function of the what we call the carrying capacity. You know, how many animals can, in the long run, survive in a stable environment. B is dependent upon the initial number of the organisms, and R is just how quickly you reach that long-term equilibrium. So you got three constants. With an exponential growth, you just had two constants, one which was dependent upon the initial value and one that was dependent upon how quickly it grew. So here's just a generic logistic growth example. So you got 2, which is, you can see that's the y value that it approaches. So it never equals 2, it approaches 2. If you let x equals 0, that's here, that's your initial amount. So if you let x equals 0, you'll get 2 plus 1 over 2 over 1 plus 2, because this goes to 1. E to the 0 is 1, so you get 2/3, and that's why that's 2/3. So that's the initial amount because of b. And then this number is always negative, and depending upon the value, it could do something like that, or it could do something like this, or it could do, it all depends. This is dependent upon some value out here in time, and it tells you how quickly it goes from the initial value to the final value. And here's J and S population curves. I'm not sure what okay. So I guess this is the J curve is probably the exponential growth. And you see it increases and it goes really quickly. The S curve, a name because it looks like an S is, I guess this is called a J curve because it looks like a J, reaches some point where you start to have environmental resistance, meaning that there is not an unlimited supply of food, or there may be disease, there may be predators, things like that. And that, as the population increases, this resistance increases and you end up leveling out to the final value. And then sometimes, like we saw earlier, it's better to fit a logarithm and the logarithm of the independent variable instead of just the independent variable, and it just allows you to see the data more easily. Instead of, if you don't take the logarithm of the independent variable, a lot of data gets smushed into a small area and it's hard to read it. So it's just easier to interpret the graphs sometimes, especially if there's an exponential relationship between the two variables. So it's y equals ax, it's usually bx plus y equals ax plus b. In this case, they put a as that's the x-intercept, the y-intercept, and you're taking the natural log. So you can either do the natural log or the log to base 10. Really, they're equivalent to each other. They both serve the same function. So what are examples of something like that? Well, this is the decibel scale. So to measure sound, you can either express the sound level in decibels, or you can do it in pressure. And if you plotted this as a function of pressure, a linear function of pressure, all these things would be smushed into a small area relative to this, because 100,000 compared to 100 million is hardly anything. So all of these would be pushed into a really small area. And also, it turns out that the decibel scale is such that there's this sound pressure, but there's also perceived loudness. And it turns out that every 10 decibels is a perceived increase in sound of 2 times. So even though I'm going from here 100,000 to a million, which is 10 times the amount of pressure variation, the decibels is only changing by 20. And 20 would be equivalent to 4 times as much, because if 10 is twice as much, then 20 is 4 times as much. So it better reflects the what you're perceived hearing difference. And you can see all these things in terms of decibel. Here's another curve. So a jet taking off 200 feet from the engine has 125 decibels. That would hurt, probably. You've got a saw, pneumatic peen hammer. These are all loud. You get to some level, you have to wear hearing protection. You're going to find you're going to get hearing loss. So there's some limits. I don't know what it is, but that's an example of a logarithmic. pH is another example. So here you have pH. So again, if you did it based on the number of hydrogen ions, you would get the end parts squished together and be very hard to differentiate between materials. But by putting in a logarithmic scale and showing that, the pH being the logarithm, after you've taken the logarithm, and you can see the different materials with the different pHs. And there's your homework.